with this question. Hopefully you're starting to kind of see just a touch. It says, what is the reaction showing solid strontium fluoride trying to dissolve in water? At least that's what this question right here is asking. So strontium fluoride solid in equilibrium with strontium ion and fluoride ion. Did we remember to put a coefficient of 2 in front of F minus? That's a good question. You don't have to answer out loud, but did we remember to put a 2 in front of F minus? Well, well, of course. Thank you. It's not diatomic. It's because strontium has a +2 charge and fluoride has a -1 charge. So I need 2 fluorides to go with 1 strontium to make it balance out. Yes. Okay, question. Okay, that would be decomposing him. And that's one of the things that the verbiage on the AP exam is not necessarily great about. Decomposition means a reaction where you're breaking him apart into his elements, not his ions. And so the correct term is dissociating or ionizing, when you're breaking him up into ions as opposed to decomposing him into his elements, no charges. And this is the one chapter where you're not used to doing this. We might have done this a teeny tiny bit back in Unit 2 with soluble stuff. And we have like sodium chloride on the left and a single arrow and sodium ion and chloride ion on the right. And that was the first time I mentioned the word dissociating or ionizing. And I haven't talked about it hardly since. So we're coming back to a part where it's always going to be breaking up into ions, not as elements. And we kind of have to get used to that because we're used to doing decomposition, especially since we just left gases. So Abby, that's okay. That's why we're doing what we're doing today and getting going on breaking him up into ions. Okay, so it says, what is the KSP expression for strontium fluoride? Ashley, what would I write down for the expression of KSP for strontium fluoride? Okay. Okay, does everybody see that? You have to square the F minus because he has a coefficient of 2. You have to square the F minus. Now, something you also have to do is make sure you put charges inside your brackets. Because we're not talking about elements now, we're talking about ions that are aqueous. Ions that are aqueous. So you've got to include your charges, yes? Yes, F and F minus are 2 different things. Fluorine and fluoride are 2 different things. And yes, fluorine can be broken apart from diatomic fluorine into 2 Fs. And that's not F minus. So they're 2 different things. Make sure you do that. All right. So if I were to do an ice chart here, I'd put 0, 0 with a big old fat Z on my left. That's only because I don't have a value and they're never going to give me a value. Because it is an amount that I have no knowledge of how much it is, but it is something other than 0. See, what you're trying to do is, it's like, best example, best picture in your mind. Is you've got a glass of water at home, and you take a spoonful of baking powder, and you dump it in your glass of water. You try to not to drink it. Stir. And it's not going to dissolve. It's not, well, tiny little bit will dissolve because it has a KSP, but it's not a pure substance. A tiny bit is going to try to dissolve, but most of it's just going to clump at the top, float, and probably not fall to the bottom like most precipitates do. And so the picture is, how did I actually go to the balance and measure out my scoop of baking powder? No, I just know it's a scoop. So my Z up there means a scoop. Don't know exactly how much, but a scoop of it. I'm trying to get it to dissolve. And I'm trying to get it to dissolve in pure water, which means I don't have any ions present initially, yes? Okay, so in my ice chart, then, I do -x plus what? 2x that will ultimately in the KSP expression get squared. Okay? That's what my ice chart's going to look like. So I'm going to have z minus x, which is approximately going to just be z, because very little of it's going to dissolve, but 0 plus x is going to be x, and 0 plus 2x is going to be 2x. Yes, ma'am? No, no, but they could ask you to find x, which ultimately, technically, is the amount of the z that dissolves, but I can find it from over here. So I really don't have to have it over here. That's why the NIMSY notes will tell you just ignore this side. And if you prefer that, if you would prefer just a bit of, put a big old squiggly through this and ignore the left side, because it always is not going to matter anyway, and just focus on the right side, that is okay, because that's how NIMSY teaches it. I can't quite do it that way because it's still part of the stoichiometry, so saying that there's nothing over here is kind of... So if you want to follow NIMSY, that's fine. You can follow it. I just can't. I have to have my little bit of info over here to help me keep the balance, if you will, equilibrium. Get it? Got it? Okay. All right, so it says calculate the KSP. Up here, here's our expression. Calculate the KSP if this many moles per liter are required to make it be saturated or make it be at equilibrium. Now notice this is the amount of X. It's not 2X, it's X. It's the amount of strontium fluoride that does fall through the cracks, creating X amount of strontium and 2X amount of fluoride. You with me? Okay. So if I go plug that into this KSP expression up here, I'm going to get X times 2X squared. Now we get the math instead. What's 2X squared? 4X squared. Okay? 2X squared becomes 4X squared. So what's X times 4X squared? What is X times 4X squared? Thank you. It's 4X cubed. That's very important that you put that in the brain, that anytime there's a 1 to 2 mole relationship between your ions or a 2 to 1 mole relationship, wouldn't matter which one comes first, you're always going to have KSP equaling 4X cubed. Always, 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 always. When it's a 2 to 1 or 1 to 2 mole relationship between the ions, you're always going to get in pure water KSP equals 4X cubed. Sometimes the X in this chapter is replaced with a little S for solubility. Doesn't matter, it's still the same thing. Still a nice chart with X. That's why I'm doing a video right now for you, Nairi. All right. So if I have the value of X, can I just go plug him in? Sure I can. Let me just grab my eraser and erase this part right here, and let's just go plug him in as KSP equals 4 times 0.0005811 molarity cubed and we get a value of like 7.8 times 10 to the minus 11. 7 point, huh? 10, okay. 7.8 times 10 to the minus 10 is my KSP value here. Okay, notice we're seeing a lot of like -5s, -6, -7, -10s, -11s. Those are more common KSP values. This -17, -33, -52, they're out there, but we don't see them quite as much. Okay? All right, one more thing. Last question. What other insoluble salts have the same ratio as 1 to 2 or 2 to 1? What other insoluble salts have this same ratio? Let me grab my handy dandy eraser. All right, so who other than strontium fluoride with a KSP at 7.8 times 10 to the minus 10, who else? Oh, Ariel, who else? Who else has a 1 to 2 or 2 to 1 ratio that's insoluble? And I'm thinking of one that's yellow. You pick one. That was mine. No, look on your KSP chart and find one that's a 2 to 1 or 1 to 2 ratio in the subscripts. Barium fluoride, good. Jordan? Lead chloride, lead 2 chloride, yes. And we'll do one more, Skylar. Calcium chloride. Calcium fluoride. Okay, calcium fluoride. All right, KSPs. This guy's like what? 1.8 times 10 to the minus 5? What's lead to iodide? 1.8 times 10 to the minus 10? Okay, so what's barium fluoride? Okay, and what, since we're right there, what's calcium fluoride? 3.4, negative 11, 3.40, okay, times 10 to the minus 11. All right, what's PbCl2? All right, Hayden, out of these choices right here, who is most soluble since they have the same mole-to-mole ratio? Lead 2 chloride is the most soluble substance here. We would get the solubility by plugging in 4x cubed, setting it equal to the KSP, and we would be finding x. But that's not what we did in this one. We were given x, all right? And so Jordan, who's least soluble? Calcium fluoride is least soluble. Now, let me make a statement. The only reason I can do this is because they have the same mole-to-mole ratio. So on the owl tonight, there's like question number 2 that says, which of these can be compared to each other? They have to have the same mole-to-mole ratio to be able to compare them to each other, just looking at their KSPs. If they don't have the same mole-to-mole ratio, can you just look at their KSPs and pick the less soluble? No, they have to have the same mole-to-mole ratio. All right, 9 and 10.